Are we doomed to remain trapped in our solar system forever? Have you ever imagined what it would be like to venture into other star systems, traversing the galaxy or even hopping from one galaxy to another? Just like in those science fiction stories, it's something that has captured our imagination since movies, TV, and books began featuring spacecraft that could break through impossible barriers. However, the idea of reaching the speed of light is much closer to fantasy than to a viable reality. And don't get me wrong, I'd love to travel among the stars and even between galaxies, but we're probably thousands of years away from that technology. Or, in the worst case, we may never achieve it, no matter how much we dream of incredibly advanced technology. The laws of physics are pretty clear. Nothing with mass can reach that speed. It's frustrating, isn't it? But the point here is to show why that limit isn't just a scientific quirk and how pop culture fuels the impression that it's simply a matter of one big discovery holding us back. Why do many people still believe that traveling at the speed of light is possible? One of the main culprits is undoubtedly the world of science fiction. Movies, series, and books tend to offer extremely convenient solutions to this challenge. Think of Star Wars, where ships jump into hyperspace as if shifting gears in a car. In Star Trek, the famous warp drive propels the Enterprise from one end of the galaxy to the other in minutes. In Guardians of the Galaxy, characters leap through hexagonal portals to anywhere in the cosmos. Even Interstellar, celebrated for its scientific rigor, ends up relying on an almost miraculous wormhole to solve the problem of vast distances in space. All of this feeds the notion that the speed of light is merely a technological hurdle, not a universal limit. The truth, however, is that the universe doesn't follow a Hollywood script. When we talk about the laws of physics, wishing or insisting won't change the facts. If something is mathematically unfeasible and theoretically impossible, no technology can work a loophole. There's no trick to cheat Einstein's relativity. To understand why our spacecraft can't accelerate indefinitely until reaching about 300,000 kilometers per second, we must face the implications of moving at extreme speeds. This limit wasn't chosen by chance. It is the very foundation of how space and time work. As human achievements overcome barrier after barrier, this time the story is different. The very nature of reality gives us a clear no-entry sign. For starters, remember that according to relativity, as an object with mass accelerates, its relativistic mass increases. In other words, the faster you go, the more energy you need to keep that pace. This creates a practical paradox. If the spaceship gets heavier, you need more fuel to continue accelerating, but more fuel means an even more massive ship, which in turn requires even more energy, and so on. Even if we had an endless fuel supply, the energy needed to reach the speed of light would end up being infinite, and it doesn't stop there. If you somehow reached that impossible threshold, how on earth would you slow down? You'd need another infinite amount of energy to decelerate, since braking in the vacuum of space costs the same amount of energy as accelerating. No energy source in the universe is sufficient to make such an adventure viable. But photons travel at the speed of light, right? Yes, but that's because they have no mass. A photon is born at light speed and stays that way forever. That's fundamentally different from a material object like a spaceship or a person. Even if by some miracle we manage to harness infinite energy, we'd face yet another problem: space. Though it seems empty, it's filled with particles and tiny bits of matter. At low speeds, a collision with these particles is almost harmless. But at extremely high speeds, it becomes deadly. Any speck of dust hitting the ship could release energy comparable to a mini nuclear explosion. The radiation from such collisions would be so intense that the hull might become radioactive, endangering everyone on board. Even if nature didn't put a stop to traveling at such speeds, the interstellar environment would tear us apart along the way. There's also a key topic we haven't mentioned yet: time dilation. The closer an object with mass gets to the speed of light, the slower time passes for it compared to stationary observers. This relativistic effect might seem like an advantage if the goal is to shorten the journey for those on board. But from the perspective of those back home, many years could have passed. For example, to reach a destination 9.5 light-years away while traveling at 95% of the speed of light, people on Earth would experience a journey lasting roughly 10 years. For the crew, thanks to time dilation, it would seem like just a bit over 3 years. Sounds great, right? But when the ship returns, it finds Earth 20 years older. This time discrepancy becomes brutal when we talk about even greater distances, such as the Andromeda Galaxy, which is about 2.5 million light-years away. If there were a way to accelerate to 99.99% of the speed of light, for the astronauts, the journey might feel like 35,000 years, but for the rest of the universe, millions of years would pass. Earth would have changed completely. Humanity might not even exist anymore, and we can't forget that even if we could build a theoretical engine that takes us to relativistic speeds, the external time interval remains enormous. In other words, the speed of light, immutable as it is, still proves slow when faced with the vastness of the universe. Just to reach the closest star beyond the Sun, Proxima Centauri, would take over 4 years at light speed, and those 4 years are measured by an outside observer, while the actual logistics of the trip could be filled with risks. When it comes to interplanetary or interstellar travel, we don't even need to get extremely close to the speed of light to notice the difficulties. Even reaching 10% of light speed would be a colossal feat. Maintaining a constant acceleration of 1 gram, which is what keeps us grounded on Earth, would already prove an almost insurmountable challenge. Today, manned missions achieve only a few minutes of acceleration to escape the atmosphere and reach orbit. Sustaining that acceleration for weeks or months would require an absurd amount of fuel and a level of physical endurance from the crew that goes far beyond what's considered tolerable. Imagine, just for curiosity, that a miraculous technology appears and provides a constant 1 gram acceleration for an entire month. To reach a certain point and then slow down would take another month of deceleration. Even with this breakthrough, the speed achieved would be far from 99% of light speed. It might be around 10% to 12% of light speed, which is still fantastic, but it leaves us very short of the goal of quickly traversing immense distances. Moreover, the available space within the solar system is nearly enough to even attempt something close to light speed. In large part, the dream of hitting the accelerator up to light speed and letting off the pedal only far ahead runs headlong into the limitations of size, fuel, and mainly the safety of the crew, and we haven't even touched on the technological aspects. If a spacecraft could travel to another system at relativistic speeds, by the time it arrived, the targeted planet's situation could already have changed. Imagine setting course for a planet that once seemed habitable only to have colonization become impossible because conditions drastically shifted in the time spent on the journey. That star might have become unstable, or the planet might have suffered a catastrophic event. The data used to aim for your destination could be outdated by decades or even centuries. Then we come to those famous concepts that people love to mention as alternatives: warp drives, wormholes, or even alien technologies that supposedly bypass the laws of physics. Physicist Miguel Alcubierre's proposal, for example, suggests creating a bubble of spacetime that expands behind and contracts in front of the ship. In theory, this would allow for faster-than-light travel without the ship technically exceeding the local speed limit. But this idea demands some form of exotic matter with negative energy, something that has never been observed, and even if it did exist, it would require an immense amount on the order of the mass of a giant planet like Jupiter, plus an energy level that's completely out of reach for us today. As for wormholes, although they are mathematically possible, they aren't stable without that same exotic matter. They'd collapse in a matter of milliseconds, and even if they lasted long enough, the radiation encountered while passing through these cosmic passages would be lethal. Then there's the whole subject of aliens. Much speculation exists if advanced civilizations are out there. Perhaps they found a cosmic workaround to travel between the stars. But, as the great Carl Sagan once said, the absence of evidence is not evidence of absence. So, until proven otherwise, we stick with what we know. The laws of nature aren't broken just for fun. It's normal for us to feel frustrated because our species has always strived to overcome seemingly definitive barriers. We've crossed oceans, conquered Earth's gravity, and even set foot on the moon. That's why we think, if it worked before, why not now? The answer lies in the unyielding nature of the speed of light. We aren't talking about a challenge to be overcome through engineering or creativity. It's like trying to form a triangle with one angle measuring 180. It simply isn't a triangle anymore. In this metaphor, time, distance, and speed are like the three angles of that shape. You can increase one, but you have to sacrifice another. Of course, for many people, we don't need to hit the speed of light to be great space explorers. There are countless current initiatives, solar sails, ion propulsion projects, nuclear prototypes that might allow us to travel much faster than we do today. Even if they're far from warp drives, that would already be an incredible leap for solar system exploration. If we managed to shorten trips to Mars, the asteroid belt, or even the region of Jupiter and Saturn, we will be making enormous scientific progress. The point is, the speed of light itself will not be surpassed, and even getting close to it demands an immense effort. Not everything is pessimistic, though. Science isn't here to shatter our dreams, but to guide our ambitions. By accepting the limits imposed by physics, we can focus on solutions that truly make sense. Maybe colonizing the solar system is achievable in the long run, and over time, we might even send probes to neighboring systems at significant fractions of light speed. But it's likely that these journeys will take centuries or even millennia, and they'll probably be robotic, relying on some super advanced artificial intelligence to keep things running. Meanwhile, humanity will continue to evolve its knowledge, and who knows, we might someday find new ways to tackle these challenges. In the end, the speed of light is more than just a number, it's the cornerstone of our understanding of space-time. There's no way to cheat without rethinking the very structure of everything that exists. It's hard to accept that we can't simply shift into high gear and cruise across the cosmos like in an adventure movie, because doing so defies fundamental laws we didn't choose but are bound to obey. Still, there's something deeply inspiring in this limitation. The quest for every extra mile of speed, for every innovation that brings us closer to the borders of the solar system or a neighboring star, depends on a collective effort that combines the curiosity of scientists, the ingenuity of engineers, the imagination of dreamers, and the persistence of visionaries. It's in this collaboration that humanity's true strength lies, not in the illusion of an immediate leap into the impossible, but in the gradual, patient, and creative work that sparks new ideas and solutions along the way. So what do you think? In 1,000 years, will the speed of light still be that absolute limit that no one can beat? Or will we discover some loophole in our laws? It's a great topic to think about, debate, and of course, keep researching. Share your thoughts. If you enjoy this kind of content, subscribe to the channel, leave a like, and share it with that friend who also loves the space world. Thanks for watching, and see you in the next video.